Good morning students. Welcome to 6th video on system of particles and rotational motion. In the previous video we learned vector product of two vectors, and in this video we are going to learn angular velocity, angular acceleration, then relation between linear velocity and angular velocity, which is a very important 3 marks question that derive the relation between linear velocity and angular velocity. So let us define what is angular velocity. See, we know that linear velocity of a body in motion is defined as rate of change of displacement with respect to time. When a body moves along a straight line, we know that the change in displacement with respect to time is called as linear velocity. But in case of rotational motion, when a particle moves from one point to another point by describing a circle with respect to an axis of rotation, then we define the displacement as angular displacement. Angular displacement is the angle swept by the radius vector in a given time. So angular displacement is the angle swept by the radius vector in a given time. Suppose if the particle moves from P to P dash in a time say dt, then while moving from P to P dash, the particle covers some angle, and that angle we call it as angular displacement. So if this angular displacement changes with respect to time, then we define that as angular velocity. Therefore, the rate of change of angular displacement with respect to time is called angular velocity. It's called angular velocity. So if d theta is the angular displacement, in time dt for a particle rotating with respect to an axis of rotation, say in this case it is z axis, in time dt, then angular velocity omega is equal to d theta divided by dt. Omega is equal to d theta divided by dt. Angular velocity is a vector quantity, and the SI unit of omega is angular displacement over time taken. So it is rad per second, because angular displacement is measured in terms of radian and time is measured in terms of second. Similarly, we write dimensional formula of angular velocity. The dimensional formula of angular velocity is m power 0, l power 0, e power minus 1. So thus, angular velocity is having the same dimension as that of frequency. That's why we write angular velocity omega is equal to 2 by mu, where mu is called frequency, or mu is equal to omega divided by 2 pi. So this is what angular velocity of a particle rotating about an axis, or angular velocity of a rigid body capable of rotating with respect to an axis. So now we define angular acceleration. So we want to define angular acceleration. See, angular acceleration is the rate of change of angular velocity with respect to time. If the angular velocity rotation changes with respect to time, then we call that as angular acceleration. So if alpha is angular acceleration, then angular acceleration can be written as alpha is equal to d omega divided by dt, where d omega is change in angular velocity in a time dt. If d omega is change in angular velocity in a time dt, then alpha can be written as d omega divided by dt. Similarly, SI unit of alpha is rad per second square. Rad per second square, that is angular acceleration is measured in terms of radian per second square, and it has a dimensional formula, that is alpha is equal to m power 0, l power 0 and t power minus 2 is. So this is about the angular velocity and angular acceleration. So now let us consider a very important derivation, that is relation between angular velocity and linear velocity, or relation between linear velocity and angular velocity. So this is a very important 3 marks question, that is they are asked derive the relation between linear velocity and angular velocity. For that, consider a rigid body rotating about an axis of rotation as shown in figure. Of course, in this case it is rotating about an axis, z axis, with a constant angular velocity omega. So we want to know what is the relation between linear velocity v of the particle rotating about an axis with that of angular velocity omega of the rigid body or a particle. Let P be a particle at a distance of course in this case it is position at or from the axis of rotation. So now if the particle moves from P to P dash in a time dt, then the linear displacement of the particle is, if the particle P moves from P to P dash in time dt, then its linear displacement, that is ds, the linear displacement of the particle, ds is equal to r into d theta. Linear displacement is position vector, magnitude of position vector into angle shown by that is ds is equal to r into d theta. We are writing only magnitude part of this. If v is the velocity, then you know v is equal to ds divided by dt. If v is the velocity of the particle, then v is equal to rate of change of displacement over time taken is nothing but velocity. This implies v is equal to ds means r into d theta, r d theta divided by dt. So we call this as equation 1 and this as equation 2. Since rate of change of angular displacement with respect to time d theta divided by dt is equal to omega called angular velocity, then equation 2 becomes v is equal to r into omega. V is equal to r omega. So this is equation 3, relation between linear velocity and angular velocity. Suppose if you want to write in vector form, we write vector v is equal to r cross vector omega. So this is the relation between linear velocity and angular velocity. Linear velocity and angular velocities are related. V is equal to r